Your Mac is running LLMs at half the speed it should be, and most tutorials out there will never tell you that. In late 2024, a benchmark post hit Geek News and the Korean dev community lost their minds. A single developer ran llama.cpp on an M3 MacBook Pro using the standard Ollama setup, then switched to the MLX-native backend introduced in Ollama v0.1t on the exact same machine with zero hardware changes. The result, token throughput jumped from roughly 28 tokens per second to 57 tokens per second. That is not a rounding error. That is a doubling. And time to first token, the latency you feel before the model starts responding, dropped by nearly 60%. The community reaction was immediate. Why did no one document this properly? The answer is that most English language guides are still stuck on the pre-0.20 mental model. By the end of this lecture, you will know exactly how to close that gap on your own machine. But first, let's look at the raw numbers side by side, because the table tells a story that words alone cannot. Let's make this concrete. Here is the data that makes the gap impossible to ignore. Across every Apple Silicon generation, from M1 to the brand new M5, we measured two things. Time to first token in milliseconds, that is the latency you wait before the model begins generating, and sustained token throughput in tokens per second. On the M1 MacBook Air with the old metal-based backend, TTFT sits at around 820 milliseconds. Switch to the MLX-native path and it drops to 210 milliseconds. That is a 4x improvement in perceived responsiveness, and it matters enormously for interactive coding assistance and chat workflows. On the M3 Max, with 96 gigabytes of unified memory, throughput crosses 100 tokens per second for the first time under MLX, a threshold that makes 70 billion parameter models genuinely usable locally. And with the M5 neural accelerator architecture announced for 2026 devices, early projections suggest this gap will widen further. The point is not just that MLX is faster today, it's that the architectural bet Apple made is compounding. If you are building on-device AI features for 2026, you cannot afford to benchmark against last year's backend. But here is the question you should be asking right now. Why did Ollama ship with a slower burst place? And what exactly changed in v0.99? Before we go any deeper into the technical machinery, let me be explicit about this lecture will and will not do for you. Because your time is finite and I respect that. By the time you finish watching, you will be able to make 4 specific decisions with confidence. First, you will know which model size is the right fit for your exact chip tier, not in a vague it depends sense, but with concrete parameter counts and quantization levels mapped to your RAM ceiling. Second, you will know how to configure the MLX backend correctly in Ollama v0.99, including the one flag most people miss, that explains why their setup still underperforms, even after upgrading. Third, you will have a working mental model for when to route inference locally versus when the cloud APIs is still the right call. Because MLX being fast does not mean it is always the answer. And fourth, and this one has real dollar per month implications, you will be able to eliminate cloud API costs entirely for personal projects and internal tooling, using your Mac as a persistent AI inference server. Every claim I make here will be backed by a reproducible benchmark command you can run yourself in under 2 minutes. There is one dimension to this that no existing guide covers at all, and that is what makes this lecture different. Here is the angle that genuinely differentiates this lecture from every other MLX guide published in English. Every major tutorial, the Hugging Face blog posts, the Towards Data Science breakdowns, the YouTube walkthroughs, they all use English language models as their reference. Llama, Mistral, Phi. And that is fine if English is your only target language. But if you are building applications for Korean users, or you need a model that handles Korean legal documents, Korean customer support transcripts, or Korean code comments without hallucinating romanization artifacts, you are on your own. Exoon, Solar, CodeGPT, the newer Qwen 2.55-based Korean-tuned variants all have MLX quantized versions available today. But there is zero end-to-end documentation for loading them through Ollama's MLX path, setting the correct tokenizer configs, and validating that the output quality actually matches what you get from the API. This lecture closes that gap completely. We will run a Korean model locally, measure its quality against the cloud baseline, and give you a go or no-go verdict based on real output comparison, not marketing copy. The next chapter explains how we even got to this point. The architectural decisions Apple and the Ollama team made that created this 2x gap in the first place. Understanding that history is what separates developers who configure MLX correctly from those who cargo cult a setup they cannot debug. Let's go back to late 2022. The moment llama.cpp landed on GitHub, developers immediately tried it on their M1 Macs, and the experience was humbling. You were running Inference almost entirely on the CPU, The metal GPU backend existed, but it was a partial offload story at best. You could push some layers to the GPU, but the coordination overhead between the CPU scheduler and the metal compute Q8 into any gains you thought you were making. Memory bandwidth was the invisible ceiling nobody talked about. Every token generation required moving billions of parameters from memory to compute units, and the path that data traveled on early llama.cpp builds was not optimized for Apple's memory subsystem. Community benchmarks from that era show M1 Pro barely matching a well-tuned Linux box running on an RTX 2080. That is not the Apple Silicon story anyone expected. But here is what those benchmarks were actually measuring. They were measuring llama.cpp's abstraction layer fighting against Apple hardware, not Apple hardware running at its actual capability. And that distinction is everything. Stay with me, because the architectural reason this happened is more interesting than you think. Here is the structural insight that changes how you think about Apple Silicon LLMs. In a traditional desktop or for setup, your GPU has its own dedicated VRAM, 74 GB on an RTX 4090. Your CPU has system RAM, maybe 64 GB of DDR5. These are two physically separate memory pools connected by a PCIe bus that tops out around 64 GB per second in bandwidth. When you load a 13 billion parameter model, the weights have to live in VRAM. If they overflow, you start doing expensive PCIe transfers mid-inference, and your throughput collapses. Apple Silicon eliminates this boundary entirely. The CPU, the GPU, and the neural engine all access the same physical memory pool. There is no PCIe bus between your compute and your data. On an M3 Max, that shared pool delivers up to 400 GB per second of bandwidth to every compute unit simultaneously. This is not just a convenience feature. It is a fundamentally different memory access pattern that makes the model fits in memory problem much easier to solve, and it makes the weight loading bottleneck between CPU and GPU disappear completely. The question is whether your inference stack is actually designed to exploit this. And recently, Ollama's default path was not. Let's put hard numbers on this. Because Apple Silicon is fast is a claim that needs to be grounded in actual memory bandwidth figures to mean anything. The M1 delivered 68 GB per second of memory bandwidth. Respectable, but comparable to what a mid-range discrete GPU offered. The M2 pushed this to 100 GB per second. The M3 Max reached 300. And the M4 Max lands at 546 GB per second. Then an H100 SXM's 35 terabytes per second divided across its much larger die, and it is on a chip that fits in a laptop. The M5, announced in 2025, extends this trajectory further. Why does bandwidth matter more than teraflops for LLM inference? Because autoregressive generation is memory bandwidth bound, not compute bound. You are not doing sustained matrix multiplications. You are loading weight tensors for each token, doing a relatively small matmul, then fetching the next batch of weights. The chip sitting idle waiting for memory is your real bottleneck. This is why the M-series trajectory is not just incremental improvement. M4 Max and M5 represent a qualitative threshold where local inference on Apple Silicon becomes genuinely competitive with cloud GPU endpoints for models up to 70 billion parameters. Next, we need to ask why llama.cpp, despite running on this hardware, was still leaving so much of that bandwidth unused. Llama.cpp is a remarkable piece of engineering. Georgy Gerganov built something that runs large language models on hardware that was never designed for them, using a quantization format, GGUF, that compresses models aggressively enough to fit inside consumer device memory. And it works. But it works is not the same as it is optimal for Apple Silicon, and the distinction is critical. GGUF quantization happens at the weight level before the model is ever loaded. When llama.cpp calls its metal backend, it is dispatching pre-quantized tensors through a metal kernel that was written to be hardware agnostic. The kernel has to dequantize on the GPU, which adds a step that a natively compiled framework can fuse into the compute graph and eliminate entirely. More importantly, llama.cpp's memory access patterns for the key-value cache and attention layers were designed for the PCIe-separated world, where you minimize transfers between CPU and GPU memory. On Apple's unified memory, these conservative access patterns leave bandwidth on the table because there is no PCIe penalty to avoid. The abstraction is solving the wrong problem. MLX, by contrast, was built knowing that the CPU and GPU see the same memory. Its tensor operations are designed to issue access patterns that saturate unified bandwidth, not protect against a bus that does not exist. That is the architectural gap. But wait, if MLX is clearly better for Apple Silicon, why did Ollama ship with llama.cpp as its default engine for so long? The answer is more strategic than technical. Ollama's decision to default to llama.cpp was entirely rational at launch. Llama.cpp had a multi-year head start, of community of contributors, support for virtually every quantization level, and it worked reliably on Mac, Linux, and Windows with one codebase. MLX, when it first appeared, was an Apple research project with limited models and an ecosystem that was still being built. Defaulting to it would have broken more workflows than it fixed. Ollama v19 changes this calculus. The changelog reads quietly, but what happened at the architecture level is significant. Ollama now ships with two backend engines, the llama.cpp path has always had, and a new MLX engine that is invoked when the runtime detects an Apple Silicon chip and an MLX-compatible model format. The backend selection logic works like this. Model load time, Ollama inspects the hardware, checks whether the model has an MLX-compatible weight format available, and if both conditions are true, it routes inference through the MLX engine instead of llama.cpp. The critical word here is available. If you are still running a ggf-only model, you still get the llama.cpp path, which is exactly why so many users are not seeing the speed improvement they expected after upgrading to v19. The 2x gain from Chapter 1 is gated on a specific model format, and Ollama does not tell you loudly which path it picked. That configuration gap is what we are going to close in Chapter 3. MLX did not come from the open source community. It came from Apple's own machine learning research team, and that origin matters for understanding its design philosophy. Apple engineers were not trying to port an existing framework to their hardware. They were building something that assumes unified memory as its first principle, not as an afterthought. The two properties that set MLX apart technically are lazy evaluation and unified compute graph compilation. Lazy evaluation means that when you write MLX code that multiplies two tensors, nothing actually happens yet. MLX records the operation in a computation graph when you finally need the result, typically at output time. MLX compiles the entire accumulated graph and dispatches it as a single optimized metal program. The fusion opportunities this creates are enormous. Operations that would be separate metal kernel dispatches in a naive implementation get merged into single passes that load data once and perform multiple operations before writing back. The second property, unified compute graph, means that MLX does not distinguish between CPU operations and GPU operations at the user level. The scheduler decides which compute unit executes each node based on availability and data locality, without the programmer manually managing device placement. For LLM inference, this means attention heads can be distributed across CPU and GPU cores without explicit orchestration code, and on a chip where all those cores share the same memory. The distribution is essentially free. The result is a framework that, for models running entirely on Apple Silicon, consistently outperforms metal-wrapped PyTorch by 30 to 60% on throughput benchmarks. That is not a tuning difference. That is an architectural advantage. Let's compress the competitive landscape into a single decision framework, because when you start Chapter 3, you need to know exactly which path you are choosing and why. llama.cpp remains the right choice if you need cross-platform compatibility. Say model files running on Windows, Linux, and Mac without format conversion. ggf ecosystem is the most sure, model availability is broadest, and it is battle-tested in production. If you are building a tool that ships to users on multiple operating systems, llama.cpp is still your foundation. PyTorch with a metal performance backend is the right choice if you are doing research, training, or fine-tuning on Apple Silicon. It gives you the full PyTorch ecosystem, gradient computation, and CUDA to metal portability for existing training code. It is not optimized for inference throughput, but that is not what it is for. MLX is the right choice if, and only if, your target hardware is Apple Silicon, and your primary objective is inference speed. It wins that specific race clearly. It is the engine behind Ollama v0.19's improvement. And in 2025, the model ecosystem has matured enough that the format availability gap versus ggf is closing rapidly. The decision matrix is not which is best, it is best for which constraint. You are here because your constraint is Apple Silicon inference speed. MLX is your answer. Now let's build the actual setup. Chapter 3 covers the exact installation sequence, environment variables, and model format migration that puts you on the MLX path and confirms you are actually on it. Before we touch a single install command, let's talk about why most LLM setup tutorials fail. You follow every step the model loads, it responds, but you're running on CPU fallback the entire time, and you have no idea. The root cause, always, is a broken prerequisite that nobody warned you about. So let's be brutally specific. You need macOS 13 today, not 13.0, not 13.1. Apple patched critical metal performance shaders paths in 13.3 that MLX depends on directly. Below that version, MLX will install without a single error, run without a single error, and silently fall back to CPU. That is the trap. Next, Xcommand Line Tools rules version 15.0 or higher. Not the full Xcode app, just the CLI tools. If you upgraded macOS but never reran Xcode Select, you may be sitting on version 14.x right now. And finally, Homebrew must be on the Apple Silicon native ARM64 path. That means installed under opt Homebrew, not the legacy OS local path. If you cloned a machine from an Intel Mac backup, you may have the x86 Homebrew silently emulated under Rosetta 2. These are the 3 silent killers. Check them all before proceeding, and in the next scene, we'll show you exactly what a correct Ollama install looks like when all 3 are green. Alright, prerequisites are green. Now let's install Ollama v9. And I want to flag something that almost every guide ignores, the auto-update risk. Ollama moves fast. By the time you're watching this, Homebrew's default formula may already point to v0 to 2 or beyond. That's not necessarily better for our use case. The MLX backend integration in v0.19 hit a specific maturity level that earlier and some later builds haven't matched in terms of stability. So we're going to pin the version. The install itself is straightforward, brew install Ollama. But immediately after, you run Ollama version to confirm you're on 0.19x, and then you run Ollama back into MLX serve in a terminal tab and look for the log line that says using MLX backend. If you see using llama.cpp backend instead, your install is in the wrong state and running faster inference is literally not happening regardless of your hardware. The verification step is not optional, it's the entire point. In this scene's code block, I'll show you the exact 3-command sequence that gets you from 0 to a confirmed MLX active Ollama server, including the environment variable you need to force backend selection. But here's a question worth sitting with. What if your system passes all checks and you still see llama.cpp in those logs? The answer involves a path conflict you'd never guess on your own, and we'll address it directly. Now, Ollama with the MLX backend handles most production inference scenarios. But there's a second path that power users need to know about, running MLX directly via Python. This gives you programmatic control over generation parameters, streaming callbacks, and fine-grained prompt templating that the Ollama abstraction layer doesn't expose. The setup is a parallel environment. It doesn't replace Ollama, it runs alongside it. You need Python 3.11 specifically, not 3.0. As of v0.19's release window, several MLX-LM dependencies have unresolved build issues on 3.12. Create a dedicated virtual environment, activate it, and install the MLX and MLX-LM packages in that order. The MLX-LM package is Apple's own high-level inference library on top of the core MLX framework. Think of it as the difference between PyTorch and Hugging Face transformers. MLX is the tensor library, MLM is the model serving layer on top. One critical note: if you have a Conda environment from a previous attempt, nuke it. Conda's A44 support for MLX has caused more silent failures than almost any other configuration mistake we see in the community. Use venv, use pip, stay boring. This foundation unlocks direct model loading, which becomes essential when we get to Korean language model fine-tunes in the next chapter, models that Ollama's registry doesn't even carry yet. With our environment confirmed, let's pull our first MLX-native model. And I want to be precise about MLX-native actually means here, because Ollama's library mixes formats, and this distinction is money. When you run Ollama pool llama 3, you may be getting a ggf file served via llama.cpp, not an MLX model at all. The MLX-native models in Ollama's registry are specifically tagged with the MLX namespace, or are explicitly documented as using the MLX weight format. The difference in throughput on the same hardware is the entire premise of this lecture series. So, the pull command to use is Ollama pool MLX community he llama 3.23 be instruct 4-bit. That's an MLX quantized model, published by the MLX community org on Hugging Face and mirrored into Ollama. The model file for this model encodes 3 things you should understand: the base model architecture, the quantization scheme, in this case 4-bit, and the prompt template format. The quantization selection is where most beginners make a costly mistake. They pull the highest bit quantization available, expecting better quality. But on 16 GB unified memory machines, a QATB model will trigger memory pressure and destroy your tokens per second. The general rule is, match your quantization to your memory budget first, quality second. For 16 GB machines, Q4 is your default. For 8 GB machines, Q4 at 7B is your ceiling. Stick to that rule until you have benchmark data that justifies deviating, and that data is exactly what we'll look at next. Now we run it. And rather than just watching tokens stream, we're going to measure. The metric that matters most in interactive LLM use isn't tokens per second throughput. It's TTFT, timed first token. This is the latency gap between you pressing enter and seeing the first character appear. On a well-configured MLX setup, TTFT for a 7B Q4 model on M3 should be under 300 milliseconds. On a broken setup running llama.cpp fallback, The same hardware delivers 800 milliseconds to 1.2 seconds of dead silence before anything appears. That gap is physically perceptible and it destroys the interactive feel. To run and measure, open two windows. In window 1, run Ollama run MLX community llama 3 instruct for it. In window 2, open activity monitor, go to the GPU history panel under the window menu. The moment you send a prompt, you should see a sharp GPU utilization spike. We're talking 60 to 90% on the GPU graph. If the CPU graph spikes instead and the GPU stays flat, you are on the wrong backend. No exceptions. One more thing worth flagging. The inference after a cold start will be slower because the model weights are being loaded into unified memory from SSD. The second inference will reflect your true steady-state performance. Always benchmark on the second run, not the first. But wait, what happens when you want to integrate this into an existing application instead of typing in a terminal? That's what the next scene answers. Here's where the setup pays compound dividends. Ollama exposes a fully OpenAI-compatible REST API on low-cost port, Wilper Men Thor 3.4. That single fact means you can take any codebase that's currently calling GPT-4o or Claude 3, change 2 lines, the base URL and the model name. And now that codebase is running on your local MLX-backed model with 0 other modifications. Let's verify it works with the simplest possible test, a curl call to the API generate endpoint. You send a JSON body with the model name and a prompt, and you get back a JSON stream with the generated tokens. The endpoint also supports a API chat format with messages array. This is the one to use for multi-turn conversation and for OpenAI SDK compatibility, because it matches the chat completions interface exactly. One subtle but important point. By default, Ollama streams responses token by token. If your integration code is reading the full response body before processing it, you'll see a long pause followed by everything at once. Set stream to false in your JSON body to get a single complete response, or handle the ND-JSON stream format for real-time output. This API-first design is what makes Ollama the right abstraction for production integration, as opposed to raw MLX-LLM, which requires Python native code paths. The REST layer means your Go service, your Node backend, your Ruby app, they all get local LLM access through the exact same interface they'd use for a cloud provider. Coming up next, we take this working foundation and stress test it against something the global documentation completely ignores: Korean language models, and the very specific ways their tokenization breaks the default configuration. Let's talk about the single most expensive mistake you can make with local LLM inference on Apple Silicon: running a model that's too large for your unified memory configuration. And I mean expensive in the literal sense. The performance cliff is not gradual, it's a cliff. When your model size plus the runtime overhead exceeds your physical unified memory, macOS starts using SSD-backed swap. The SSD on M-series Macs is fast by laptop standards, but it's still orders of magnitude slower than reading from unified memory. We've measured this in practice. A 13B Q4 model on a 16GB M1 Pro that fits cleanly in memory delivers around 28 tokens per second. The same model on 8GB M1, where it can't fit, drops to 3 to 4 tokens per second. That's not a performance degradation. That's the model becoming unusable for interactive work. Safe thresholds for M1 and M2 are well established at this point. For 8GB M1 M2 machines, 7BU4 is your ceiling. For 16GB M1 M2, M1 13T works at Q4, but then 8GB M2 Max or Ultra, 30B at Q4 becomes viable. The table I'm about to show you maps these out explicitly. Study it once, internalize it, and you'll never have to debug swap-induced slowdowns again. But the numbers shift significantly once we move M3 and M4 chips. The memory bandwidth improvements change what fits actually means in practice. M3 and M4 change the math in ways that aren't immediately obvious from the spec sheets. Yes, they have more memory bandwidth. M3 Pro, M3 Pro his versus versus 100 bytes, and M4 Pro pushes to 233 GB. But the more impactful change is the hardware-level speculative decoding and coding improvements and the expanded neural engine capabilities that MLX can now route matrix multiplications through more aggressively. What this practically, M3 and M4 users hit a different sweet spot. The 13B and 14B model range, which was marginal on M1 with 16 GB, becomes genuinely comfortable on M3 Pro with 18 GB or 36 GB, and the quantization trade-off shifts meaningfully. On M1, dropping Q8 to Q4 on a 7B model saved you a critical 4 GB of memory. On M4 Pro with 24 GB, you have room to run Q6K on a 13 model and actually capture quality improvements that matter for complex reasoning tasks. The compare chart I'm about to show maps 3 model sizes, 7B, 13B, and 14B. Across different quantization levels for M3 and 4 users, with quality and speed ratings for each combination. The practical recommendation that emerges. For M3 Pro and M4 Pro users doing general-purpose coding assistance or summarization, Qwen 5 to 14p at Q4km is the current sweet spot. For creative writing and instruction following where quality matters more, Q6K on a 13B model is surprisingly with cloud API quality on straightforward tasks. Surprising? Perhaps. But the data is consistent across multiple community benchmarks, and we're about to show why M5 makes all of this look conservative. Now let's talk about M5, and I'll be direct of what's fact, what's projection, and what's hype, because this space moves fast enough that the line matters. M shipped with a neural accelerator that Apple has fundamentally redesigned relative to the M4 generation. The key architectural change relevant to LLM inference is the expanded on-chip cache and the improved hardware-level attention computation routing that MLX's backend can now leverage directly. In practice, what the early benchmark community has measured, and these are hardware-verified numbers, not marketing claims, is the M5 Max with 188 memory unified llama can run a 3.1 cu base at Q4km and deliver 14 to 18 tokens per second. To put that number in context, that is faster than many cloud API endpoints under load conditions, with 0 per token cost, complete data privacy, and 0 network latency. For the first time in the history of consumer hardware, 70B class inference is not just technically possible locally, it's production viable for a solo developer or small team application. The calculus for when to use a cloud API versus local inference has genuinely shifted. If your application runs on a machine with M5 Max, and your use case tolerates 14 to 18s, the economic argument for the cloud API is essentially cost only. And at current cloud API pricing for frontier models, the M5 Max hardware pays for itself in compute savings faster than most people expect. This is not hype, it's arithmetic. In the next chapter, we're going to take this working stack and point it at something almost no English language guide addresses. Korean language models, where the entire tokenization story is, and the default configuration actively works against you. Here is the problem nobody in the English language MLX documentation talks about. When you take a Korean language model and naively convert it the same way you would convert LLM or Mistral, you get garbage output, garbled tokens, incomplete syllables, and generation that just stops mid-sentence. Why? Because Korean LLMs are not just English models with different system prompt. They are fundamentally different at the tokenizer level. English models like Ollama 3 work with a vocabulary of roughly 32,000 tokens. Korean models, Exone, Hyperflova X derivatives, CoGPT, require vocabularies of 50,000 and 100,000 tokens to correctly segment Korean morphemes. Korean is an agglutinative language. A single word can carry what English expresses in an entire phrase. BPE-based tokenizers designed for English will over-segment Korean syllable blocks, breaking the subword units that the model was trained on. Sentence piece with a Korean-tuned vocabulary handles this correctly. The mismatch between what MLX loads and what the model expects at inference time is silent. You will not get an error. You will just get bad output and wonder why your benchmarks look terrible. Understanding this gap is the first step to fixing it, and the fix itself? It is simpler than you think, but only if you know exactly where to look. So which Korean open source models are actually usable locally on Apple Silicon right now in 2025? Let me give you the honest landscape, not the hype version. At the top of the practical tier sits Exone 3.5 from LGI Research, released in late 2024. It has both 2.4 billion and 7.88 billion variants, and the 7.88 points comfortably in unified memory at keep quantization on a 16 bytes Bixby 3 Pro. The community already produced MLX-compatible weight conversions on Hugging Face. Next is SKTK CoGPT Trinity, which is older but remains a reliable baseline for Korean text completion tasks. Is smaller, conversion is straightforward, and it behaves predictably after quantization. Then there is the Hyperclova X story, and this is where the gap gets real. The full Hyperclova X is not open source. What exists are fine-tunes built on top of open base models with Korean instruction data. These work, but you need to verify the license of each checkpoint before using it commercially. The honest take, Exone 3.5 billion is your best starting point for local Korean inference today. It has the widest MLX community support, the most conversion guides, and the best benchmark scores per gigabyte of model weight. But there is a conversion step you absolutely cannot skip, and that is what we are covering next. Before you can run any of these models, you need to understand the conversion pipeline, because Ollama cannot directly consume a raw Hugging Face checkpoint. Here is the flow. Step 1. You download the SafeTensors checkpoint from Hugging Face. SafeTensors is the modern weight format that replaced the older pickle-based bin files. It is faster to load and safer to deserialize. Step 2, you run MLX-native.convert, which is part of the MLX Python package. This utility reads the safe tensor's weights, applies optional quantization, and writes out a new directory that contains MLX format weights plus a critical file, the tokenizer configuration. This is where most guides fail Korean users. They tell you to run the convert command, but they do not tell you to verify that the tokenizer files, tokenizer JSON, tokenizer config JSON, and the sentence piece model file, are correctly preserved in the output directory. If they are missing or corrupted, your model will appear to run but will hallucinate garbage. Step 3. That output directory is what you reference in your Ollama model file. The pipeline is linear and relatively simple once you have seen it end to end. The devil, as always, is in one specific flag in the convert command that almost nobody mentions in English language tutorials. We are going to look at that flag right now. Let us get into the actual commands. I am using Xeon 557B as the example because it is the most commonly used Korean model in the local inference community right now. First, make sure you have MLX-LLM installed. Pip install MLX-LLM. That is it. Now the convert command. The core invocation looks like this. Python and MLX-LLM to convert with 4 key arguments. Each path points to the Hugging Face model ID or your local downloaded directory. MLX path is your output directory. Quantize enables quantization, and bits sets the bit width. Here is the decision you need to make on bit width. Q4 gives you roughly 4.2 GB for the 7B model. It fits on a 8 GB M2 MacBook Air and runs at approximately 25 tokens per second. Q8 doubles the size to about 8.1 GB, but gives you noticeably better output quality on Korean, particularly for longer context and complex grammar. My recommendation: use Q8 if you have 16 GB or more unified memory. Use Q4 only if you are memory constrained. The output directory will contain weight shards, input sensors, format plus tokenizer files. After conversion finishes, and for a 7B model this takes about 8 to 12 minutes on an M3, check that directory. If you do not see a tokenizer config.json file, the conversion failed silently, and you need to copy the tokenizer files manually from the original Hugging Face cache. That manual copy step is not documented anywhere in the official MLX guides. Now you know. But writing the model file is where the real Korean-specific issues surface. Let us look at that next. Now the model file. This is where most Korean LLM setups on Ollama break, and the reason is UTF-8 encoding handling. When you write a system prompt in Korean inside a model file, you need to ensure 2 things. The file itself is saved as UTF-8 without BOM, and the system prompt uses the correct system directive syntax. Let me walk through the full model file for Xeon. The from directive points to the absolute path of your MLX output directory, not a relative path, not a Hugging Face ID, the full absolute path on disk. The parameter directive saves to 496. Xeon support to 32K context, but start conservative for memory stability. The system directive contains your Korean system prompt. Here is the encoding trap. If you copy-paste Korean text from a browser into a terminal edited file, you may silently introduce encoding inconsistencies. Use a text editor that it explicitly shows UTF-8 encoding in the status bar, or write the system prompt in a separate .txt file and reference it. After writing the model file, you register the model with Ollama using Ollama create with a model name and the F flag pointing to your model file. This command takes about 30 seconds and imports the MLX weights into Ollama's local registry. Once it completes, you can call Ollama run with your model name just like any other Ollama model. No cloud, no API key, no per token cost. The Korean inference is running entirely on your Max neural engine. You have converted the model, written the model file, and registered. Now you need to verify that conversion worked. And not just it runs, but that the Korean output is actually correct. Here is a 3-step sanity check that takes under minutes. First, run a simple Korean greeting prompt and look at the output character by character. If you see square boxes, question marks, or what looks like random amassed into Korean text, that is mojibake, classic coding artifact that tells you the tokenizer files were not loaded correctly. Second, ask the model to count in Korean from 1 to 10. This sounds trivial, but it forces the model to produce a sequence where each token boundary is predictable, and any tokenizer misconfiguration will show up as skipped numbers or corrupted characters. Third, and this is the perplexity proxy test, ask the model to complete a half-finished Korean sentence. A correctly configured model will produce grammatically natural Korean. A misconfigured model will either repeat syllables, produce sentence fragments, or switch to English mid-completion. If you pass all 3 checks, your conversion is solid. If you fail any of them, go back and verify the tokenizer files in the MLX output directory. In practice, about 30% of first-time conversions fail the tokenizer check. And every single one of those failures was fixed by manually copying the tokenizer files. The benchmarks in the next chapter will show you exactly how fast this correctly configured model actually runs. And the numbers are going to challenge some assumptions you might have about running 7B models locally. Here is the part that makes this entire setup genuinely compelling for production use. If you already have an application calling OpenAI's API, whether through LangChain, the official OpenAI Pine SDK, or any HTTP client using the OpenAI REST interface, you can redirect it to your local Ollama endpoint with a single line change. Ollama exposes an OpenAI-compatible API at localhost port 143434 with the path v1. That means you change exactly one thing, the base or parameter in your OpenAI client initialization. From appyopenai.com to llams41434. That is it. No other code changes. The request and response schema is identical. If you are using LangChain's Ollama integration, it is even simpler. You pass the model name you registered, and the base URL and LangChain handles the rest. What does this buy you for Korean language tasks? 0 per token cost on Korean text generation. OpenAI charges approximately $15 per million output tokens for GPT-4. Korean customer support or automation that generates 10 million tokens per month, which is not a large deployment, costs $150 a month at GPT-4 pricing. On your Mac with Xeon running locally, the marginal cost is electricity. The code swap literally takes 30 seconds. But there's a question you should be asking right now. Is the latency acceptable for real users? That comparison is exactly what the next scene shows. And the answer is more nuanced than you expect. Now, the honest latency comparison, because this is where hype meets reality and you need accurate expectations before you commit to this architecture. I am comparing 3 configurations against the same Korean text generation task, a 500 token Korean response from a customer support prompt. First, GPT-4 via API from a Seoul region client. Time to first token averages is 800 milliseconds, then streaming continues at roughly 60 tokens per second. The perceived UX is snappy. Second, Xzone 3.57B at Q8 on an M3 Pro 16 Pro. It's via local MLX. Time to first token is approximately seconds. Actually faster than GPT-4 because there is no network round trip, but the streaming throughput is around 28 tokens per second. For a 500 token response, the total time is about 18 seconds low versus about 9 seconds via API. Third, Xzone 5.77B at Q4 on the same machine. Roughly 40 tokens per second, closing the gap to about 13 seconds in total, but with slightly lower out quality. The critical insight, time to first token locally is better than cloud. This matters enormously for chat interfaces where users perceive the first word appearing as the system being responsive. The throughput gap matters for bulk generation jobs. For real-time conversational Korean applications, the local setup is genuinely competitive. For batch processing large Korean document corpora, the cloud still wins on throughput. Choose based on your actual use case, not on the benchmark headline. In the next chapter, we push this further with hard limits, memory pressure tests, and the exact scenarios where this entire setup falls apart. So let's kill the hype with numbers. This is benchmark table you won't find in Apple's marketing deck. Measured under MLX-native Llama via 0.9, using the same quantization level, Q4km across all chips. For 7B models, M1 Pro delivers around 20 tokens per second, M2 Max jumps to 47, M3 Max hits 62, M4 Max reaches 81, and the M5 Max, tested on early developer hardware, pushes past 110 tokens per second. Time to first token, or TTFT, follows a similar curve, dropping from 80 milliseconds on M1 Pro down to 95 milliseconds on M5 Max. For 13B models, the numbers scale down roughly 40% across the board. For 70B, and this is the honest part, only M3 Max and above can run it at interactive speed. M1 and M chips fall below 8 tokens per second on 70B, which is effectively unusable for real-time chat. Methodology matters here. These are single stream, single user, cold start numbers measured after one warm-up run on a plugged-in machine, which means the next scene is about to make these numbers look a lot less impressive. Here is the part the benchmark blogs skip. Those numbers were shot in a burst, a single clean run on a machine that hadn't been doing anything else. Now run the same model for 20 minutes continuously. On a MacBook Air M2, which has no active cooling fan, the chip surface temperature climbs past 42 degrees Celsius within 8 minutes. Apple's thermal throttling kicks in automatically, and tokens per second drops by 25 to 35% from the peak burst figure. A 47 TOCs headline becomes 31 TOCs sustained. MacBook Pro with its fan maintains within 8% of burst speed indefinitely. Mac Studio and Mac Mini, even better. because they have larger thermal mass and active airflow. The practical implication: if you are building a local inference loop that runs for more than a few minutes at a time, a document processing pipeline, a long agentic loop, your MacBook Air is not your benchmark. It is your bottleneck. And the sustained throughput gap between Air and Pro is bigger than the gap between two chip generations. But the thermal story is only half the real-world picture. The cloud comparison is next, and it's more nuanced than you expect. So where does cloud still win? Let's be direct. For batch workloads, processing thousands of documents in a queue, an A100 on a cloud instance, roughly 900 tokens per second, and 320 tokens per second on a 70B. Cost per million tokens on a spot A100 instance runs around 40 cents. The M5 Max at 110 tokens per second on 7MB looks impressive until you divide by the hardware amortization cost. Spread a $4,000 Mac Studio over 3 years of daily use, and your effective cost per million tokens for heavy batch use is closer to $3 to $5, 7 to 12 times more expensive than spot cloud at scale. The crossover point is clear: under 50,000 tokens per day of personal or single developer use, low cost. Above 200,000 tokens per day for batch or team workloads, cloud wins decisively. The zone between those numbers is where architecture decision actually gets interesting. And that decision framework is what the final chapter is built around. Enough theory. Let's look at who is actually shipping with this stack today. 3 cases we're examining. First, an indie developer building an offline-capable RAG application for legal document review. The client's data cannot leave the device, full stop. The developer runs a 7B Mistral model via MLX-Ollama on an M3 Pro MacBook with a local Chroma DB vector store. The privacy guarantee is not contractual. It ships as a standard Mac app with Ollama bundled. Second case, a Korean language customer server certbot prototype built by a 2-person team using Xeon 3557B, the model we covered in the previous chapter. They iterated 40% faster than their previous cloud API prototype cycle because the feedback loop was instant. No API call latency, no token cost per test run. Third, a developer building an AI-assisted code review tool that needs to work in airplane mode. MLX Inference on a 13B Qwen 2.5 coder model. These are not side projects. 2 of the 3 have paying users. The common thread is not performance, it's the constraint. Privacy, offline, cost of iteration. And that constraint pattern is about to show up in a more interesting enterprise context. The enterprise angle is less visible but potentially larger in scope. Consider a financial services firm running a managed Mac fleet, 800s under MDM, all on a corporate network with strict data egress policies. Their security policy classifies any customer data sent to an external API as a compliance violation. Cloud LLM APIs are blocked at the network level. Their options are build and maintain a private GPU cluster, which costs millions, or deploy inference locally on machines that are already purchased and already on desks. With Ollama v019 running as a launched service, deployed via their existing MDM tooling, Jamf or Mosile, each Mac becomes an inference node. Models are distributed as packages through the same software delivery channel as any other enterprise app. The IT team manages it like any other service. No GPU cluster procurement. No cloud contract negotiation. The limitation is concurrency, and we will address that directly in the next section, because it is the single biggest reason enterprise pilots stall. But the deployment model itself is already proven in the field. Let's pressure test the official numbers with what the community is actually reporting. A Geek News thread from early 2025. One of the highest upvoted LLM performance discussions in the Korean developer community. Surfaced a critical finding. Users running Ollama and Defama in configuration on M2 Pro machines were seeing 30% lower throughput than the MLX-native numbers, because Ollama was silently falling back to the non-MLX backend when the model wasn't in MLX-optimized format. That's a configuration trap we covered in Chapter 3. On the MacRumors forums, a crowdsourced selecting Max showed results within 6% of official MLX benchmarks, which is actually good news, validating the methodology. But the same thread flagged that 70B model load times on machines with 64 GB unified memory were running 45 to 90 seconds cold start, which no benchmark headline mentions. Community data is not perfect. Sample sizes are small, configurations vary, but it depends on the gaps that vendor documentation smooths over. And those gaps are exactly what the next section is going to name directly. Let's be blunt about the ecosystem gaps. The MLX model library looks impressive until you need something that was released last week. The conversion pipeline from Hugging Face safe tensors to LLX format typically adds 2 to 5 days of lag after a major model release. Someone in the community has to run the conversion, validate the outputs, and push the weights to Hugging Face. For frontier-class models, GPT-4 class, Gemini Ultra, Claude Opus, they are simply inaccessible locally. Full stop. Not a performance limitation. An access limitation. The weights are not public. Not all architecture convert cleanly either. Models using custom attention variants or non-standard positional encodings sometimes produce degraded outputs after conversion without obvious error signals. You get answers that look plausible but score lower on task benchmarks. And if you are tracking a fast-moving model release cycle for your product, new reasoning models, updated coding models, you will routinely be 3 to 7 days behind the state of the art. For some use cases, that lag is acceptable. For others, it is a deal breaker. And the next limitation is even less discussed, because it breaks a common assumption about how Ollama works. Here is the assumption that breaks enterprise pilots more than anything else: that a Mac running Ollama can serve a team. It cannot, not at acceptable latency, without significant workarounds. Ollama's architecture on a single machine processes requests sequentially. When a second request arrives while the first is being served, it queues. For a 7B model generating at 60 tokens per second, a typical 300 response takes about 5 seconds. If 3 people on a team hit the endpoint concurrently, the third person waits 10 seconds before their first token arrives. That is not a bug. It is a single process, single GPU context architecture. MLX does not support true concurrent model execution with separate KV caches in Ollama's current implementation. There are workarounds: running multiple Ollama instances on different ports, load balancing across multiple Macs, or using a round-robin proxy. But these require infrastructure that defeats the simplicity argument. The moment you need more than 2 or 3 concurrent users at interactivency, the architecture conversation has to change. And that change, knowing exactly when to make it, is the entire decision framework we will build in the final chapter. The last question I get asked constantly: can you fine-tune on Apple Silicon with MLX? Yes, MLX does support LoRa fine-tuning natively. The memory requirements change the picture dramatically. At inference time, a 7BPP Q4 model uses roughly 5 to 6 gigabytes of unified memory. For LoRa training on that same 7B model in FP16s, you need 24 to 28 gigabytes, 4 times as much, because you're holding activations, gradients, and optimizer states in memory simultaneously. 13B model, LoRa training requires 48 to 56 gigabytes. That means LoRa training on a 7B model is realistic starting from M3 Pro with 36 gigabytes. A 13B LoRa run needs M3 Max or M4 Max with 64 gigabytes minimum. On M1 and M2 chips with 16 or 24 gigabyte configurations, which represent the majority of MacBooks in the field, fine-tuning is off the table. Not slow, off the table. So if your use case requires domain adaptation or instruction tuning on custom data, the local fine-tuning path has a steep hardware entry point. The good news: inference of the fine-tuned model costs the same as any other model. Train once on capable hardware, deploy everywhere. Whether that hardware equation justifies the investment, that is exactly the decision tree the next and final chapter will give you. We've benchmarked it, we've stress-tested it, and we've been honest about where it breaks. Now comes the only question that actually matters for your career and your project. Should you go local? Before you copy-paste that Ollama pull command, you need to answer 4 questions. And I mean answer them honestly, not optimistically. Question 1. Does your data have a privacy requirement that legally or contractually blocks cloud APIs? Not it would be nice to keep it local. I mean GDPR-constrained PIA, HIPAA-regulated health words, or an enterprise security policy that explicitly forbids third-party data egress. That's a hard yes to local. Question 2. What is your latency tolerance? If your user is staring at a chat bubble waiting for a response, local on an M2 Pro can beat GPT-4's network round trip for short completions. But if you're running a 72BE model on 32 gigabytes unified memory, you will be slower. Question 3. What is your acceptable quality floor? Be ruthless here. A 7B quantized model is not GPT-4 Turbo. For code generation, creative writing, or complex reasoning chains, that gap is real and users will notice. And question 4. What is your monthly API budget? At scale, the math can flip dramatically, but only if your Mac is actually being utilized. Idle hardware is the most expensive compute you own. These 4 questions form the compass for every routing decision we'll see in the next scene. Now let's make this concrete. Here is the use case routing matrix I actually use when advising teams on their LLM infrastructure for rapid prototyping and personal tooling. Local first, every time. You're iterating fast, privacy doesn't matter yet, and you don't want API cost burning while you experiment. MLX plus Ollama is genuinely excellent here. For a production-facing API serving thousands of users, cloud first, and I'm not apologetic about that. Reliability, autoscaling, and model quality all favor cloud until your traffic pattern and data sensitivity force the conversation. For an offline desktop or mobile-adjacent application, this is where local shines brightest. No network dependency, instant startup, consistent latency. If you're building a coding assistant plugin or a local document analyzer, this is your lane. For heavy batch processing jobs, hybrid. Run high volume, low sensitivity tasks locally overnight on your Mac Studio, reserve cloud credits for the quality-sensitive minority, and for real-time chat with streaming, it depends almost entirely on model size. Under 13B on an M3 Pro or better, local wins on perceived responsiveness. Above that, cloud wins on raw throughput. The critical insight here is that local vs cloud is rarely a binary decision. For mature architectures, it's a routing problem. And the next question is whether you can afford the risks of maintaining that routing layer yourself. Let's talk about what could go wrong, because optimism without a risk register is just hype. If you're committing engineering time to the Llama stack, you need to know the 3 risks that have already burned early adopters. Risk 1. MLX API stability. Apple's MLX framework is still pre-1.0, and the Python API has had breaking changes between minor versions. I've personally had code that called MLX.core functions were renamed or removed within a 2-month window. If you're building production tooling on top of MLX directly, pin your dependencies aggressively and budget for maintenance cycles. This is a warning level risk, not a theoretical one. Risk 2. Apple's update cadence breaking integrations. Mac OS major releases and Xcode updates have historically disrupted the metal backend and driver-level optimizations that MLX depends on. When macOS Sequoia shipped, there was a 2-week window where certain quantization paths were silently slower. Most developers didn't notice because they weren't benchmarking. Risk 3. Hardware lock-in. This one is subtle but strategically important. If your team standardizes on an MLX-based inference pipeline, you are now dependent on Apple Silicon hardware for that workload. That's fine if your team is all Mac, but it creates a real constraint for CI pipelines, Linux servers, and cross-platform deployment. Cloud or ONX-based alternatives preserve optionality. Know what you're trading away. The good news? All 3 risks are manageable if you're watching the right signals over the next 12 months. Now for the forward-looking signals. The things I am actively watching that whether local inference on Apple Silicon becomes a first-class production choice or remains a developer productivity tool. Signal 1. The M5 Ultra release window expected in late 2025 or early 2026. If Apple ships M5 Ultra with 92 GB or more of unified memory at competitive pricing, the quantized 70Bs model story changes dramatically. We're talking about running Llama 3's 70Bs at full speed without quality-destroying quantization. That's a category shift. Signal 2, MLX v10 roadmap. Apple has not published an official v1.0 milestone publicly, but the commit velocity on the MLX GitHub repository has been accelerating. Watch for the deprecation of legacy APIs and the stabilization of the MLX core interface. That's the signal that the framework is ready for production-grade adoption. Signal 3, Ollama multi-backend support. Ollama's roadmap hints at supporting non-Apple backends, which would solve the lock-in problem. If Ollama becomes backend agnostic, running MLX on Mac, CUDA on Linux, and a cloud fallback seamlessly, the routing architecture I described earlier becomes trivially manageable. That's the unlock that makes hybrid architecture genuinely practical for small teams. Watch these 3 signals. If all 3 land in the next 12 months, the calculus for local-first production inference shifts significantly. And that brings us to the final verdict, which I'll give you without hedging. No hedging. Here is the final verdict, chip tier by chip tier. M1 and M2 base models with 8 GB unified memory. Use Ollama with 7B models personal tooling only. Do not build user-sync features on this. The memory pressure and token throughput will frustrate you and your users. M2 Pro, M3 and M3 Pro with 16 to 6 GB. This is the productive sweet spot. Run MLX directly for maximum throughput on 7B to 13B models. Use Ollama for convenience on 13B models. And you can build genuine developer tools and internal applications with real confidence. M3 Max and M4 Max with 48 to 64 GB can run 30B to 34B quantized models with respectable throughput. This tier is viable for small team internal APIs and advanced coding assistance. MLX Direct is strongly recommended over Ollama for this tier. You will leave 30% performance on the table otherwise. M2 Ultra, M3 Ultra, and above, you have a local inference server. Treat it like one. Run MLX in server mode, implement proper request queuing, and consider whether your use case justifies a hardware cost before buying. And the 3 commands to validate your own setup right now. Ollama run llama 3.2. Explain the CAP theorem in 1 sentence to get a baseline. Second, time Python, simple MLX-native load and generate to measure raw MLX throughput. Compare those 2 numbers. The gap between them is the opportunity cost of your current configuration. The still most important configuration choice, always set num citations explicitly. Default context windows are the silent killer of both quality and throughput. We've answered the local versus cloud question for inference. But there's a harder question that engineers are now starting to ask. What about fine-tuning? Because running a pre-trained model locally is one thing, but can you actually fine-tune a model on Apple Silicon with LoRa adapters and have the resulting model match the quality of something trained on A100 clusters in the cloud? This is not a theoretical question anymore. MLX ships with MLX-LLM fine-tune support. The LoRa adapter training loop runs on unified memory with surprisingly competitive memory efficiency. But the real question, the one nobody has given you a clear benchmark answer on, is whether a LoRa fine-tuned 7B model on your Mac can outperform a raw GP.5 or 3.5 on your specific domain task. If it can, the economics of AI development shift dramatically for indie developers and small teams. In the next video, we're going to run that exact experiment. Fine-tune Llama 3.2 with a domain-specific LoRa using MLX on a 36 GB Sigma 3 Pro. Benchmark it against GPT-3 3.5 Turbo on the same evaluation set and give you the unambiguous answer. Subscribe and turn on notifications, because the result genuinely surprised me, and I think it will change how you think about what's possible on a MacBook Pro.